Today we're embarking on the insane task of trying to find the greatest common factor, call it the GCD, I guess. Sometimes you see it called the highest common factor. HCF, highest common factor, is common these days, I think. Means the same thing. Highest common factor, greatest common divisor mean the very same thing. Okay. Now I'm going to let this symbol refer collectively to the greatest common divisor of all 2025 terms. And yes, there's 2025 of them. We start at 0 because it leads to an easy computation. We go out to 2024, so that is 2025 terms. Now, certainly directly listing the decimal expansions is next to impossible. Even it'd be tough for a computer, I think. So we got to come up with some clever ways of doing this that deal with modular arithmetic. Now, again, the easiest to compute term is the first term, the 0th term. And when you do that, you get this. Now, this proves the 187 has only two prime factors, but more importantly right now, it proves that the GCD must be, and that's just based on the definition of the GCD must be less than or equal to 187, which really is a minor accomplishment because you know how big the rest of these numbers are, right? I mean, this is just the first one. The very next term, b to the first, would be 5 to the 33rd power. So you see, that's already a huge number, and you're adding other huge numbers. So we already know the GCD has this upper bound of 187. And the fact that there's only two prime divisors will guide our thinking here. What we do right here is consider all the multiple cases that's based on Fermat's little theorem. Let me write that down. Very popular result. It states that a raised to the p minus 1, where p is prime, is congruent to 1 mod p. Okay. So that condition really helps us out a lot, because you see what we do right here. We got the 16 going on, which is 1 less than 17, and we have the 10 going on, which is 1 less than 11. So we just applied Fermat's little theorem multiple times to get these useful results for the computations that follow. Okay. Now, so here's a general b to the n term. Okay, and we already know what b to the 0 is, but the result holds up for all non-negative integers, I think. It definitely positive integers, non-negative integers, I think. Now, you can see the work here. What we did, we exploited the fact that 5 to the 10th is congruent to 1. 5 to the 10th, you can just put a 1 here if you want to, from a standpoint of congruences. Now, at this stage, it's still an equality. But when you come down here, you can see why all that's left is the 5 cubed, right? Because this 5 to the 10th is congruent to 1 no matter what you raise it to. It's raised to the 3 to the n, but who cares? So again, we're taking advantage of the fact that 5 to the 10th is congruent to 1 modulo 11. And the same kind of thing happens with base 7 and base 13, all right? And so you get this nice result, which looks very familiar, but what's nice about this? This is for all n, right? This is for all n, and so that implies that the GCD, or wait, let's put it this. Let me just write this down. That proves that b to the n power. Okay, I was thinking about writing down a stronger statement. 11 divides b to the n. Let me write this. Hopefully I got myself painted into a corner here. 11 is a divisor of b to the n. All right. For all n. Now this is kind of strange looking. This is just for the first, but we've actually shown right here that 11 divides b to the n for all n in the problem. And when I say for all n, I mean n up to 2024. Okay. So anyway, that's some good news. You know, we know that for a fact. However, we don't know anything about 17 yet. So let's see what happens with 17. Okay, now continuing in a similar fashion, we have this statement. Okay, and at this stage, we're just using the result of 16 here. We were motivated right here to split 30n into 16n and 14n. Remember, this is just laws of exponents, right? B to the A, let me write this down. B to the A, uppercase B, B to the lowercase b. You just sum, okay, is equal to B. That's all that happened right here. Is equal to B to the A plus B, right? It's at first you're not, I was going, oh, what? But it works, right? See, 16 and 14 does add up to 30, right? Okay, but notice that 5 to the 16th, 7 to the 16th, and 13 to the 16th are congruent to 1. So you see how the 5 to the 16th goes away right here. The 7 to the 16th goes away right here. That's very nice. We get this result here, but we're still kind of stuck, or at least I was kind of stuck. I didn't really know how to proceed with this, but it's valid just to look at one number, because if one of the numbers, one of them is not divisible by 17, you can rule out 17 as being, you can rule out 17. All right, and so that would just mean that the GCD is going to be 11, right? Because we found one term that's not going to be divisible by 17, and that's exactly what I do on this very next line. Again, where does this come from? Well, again, 5 to the 16th is congruent to 1. Okay. And so you can see why there's just a 5 left right here, right? There's a 5 left here. We ripped out 5 to the 16th, and all we're left with is 5. And 7 to the 16th is just congruent to 1, right? That's why we have a 1 here. Now, 13 to the 15th was a little trickier. And y'all, let me show you how it worked with that. 13 to the 16th, by Fermat's little theorem, is congruent to 1. And, of course, we're talking mod 17. All right? Now, how do we get to 4 right here? Well, notice that 13 to the 4 times 13 is congruent. Let me just write this down. 4 times 13 is congruent to 1. Again, y'all, I'm leaving out the 17, but it's mod 17. 4 times 13 is 52. 52 minus 1 is divisible by 17. 51 is equal to 3 times 17, right? So you see, that's what I did right here. Since this is just congruent to 1, this, when you multiply through by 4, you will get 13 to the 15th. Isn't that cool? So that's what they call a multiplicative inverse, I believe. So we get 13 to the 15th is congruent to 4. Otherwise, I wouldn't know how to do that very easily. You know, it would be kind of painful to do that, you know. So that's where this 4 comes from, right? That's why I was proud of that. That was green. So, but notice that 10 is not congruent to 0. So that means 17, let me just write this down. A lot of work here, but to me it's worth it. 17 does not divide, negated relation, b to the first, right? So what is this? All of this leads to the fact that we know that we know from here that 11 divides b to the n for all n, right? But 17 does not divide one of the b's, right? So what does that force the GCD to be? That forces the GCD to be 11. And y'all, I'm sorry I don't have this on one screen, but all the pieces are in place. So the GCD of all 2025 of those numbers is indeed 11. And let me know if you know how to do this. I looked at this trying to do this for the general case, and I thought it was just easier to find 1. If you find 1, that's good enough, right? Because the GCD, every number counts in the GCD, right? The greatest common divisor. So anyway, that is the solution, folks. GCD is not congruent to 11. It's equal to 11. Sorry about that. So the GCD is equal to 11. All right, I'll come up and put it at the top. So the GCD of all 2025 terms. To me, it's amazing. Try just doing that without modular arithmetic and see where you get. Maybe somebody, a Python coder, might figure this out. Thank you for viewing.